Welcome back to Hypnosphere, a quiet channel where we let science unfold at the pace of breath. If you feel comfortable, tell me where you are listening from and what time it is for you. I like imagining the map of listeners as a soft glow along coastlines and river mouths, mountain towns and inland lakes, each place with its own water story. Tonight we will travel with the moon, not across the sky, but through the oceans. We will explore how a distant companion reaches into the seas and lifts them, not with hands, but with a field that acts everywhere at once. The tides are one of the oldest rhythms on Earth. They are regular enough to set a clock by, and mysterious enough to reward a lifetime of looking. You already know the outline. The moon pulls on the ocean, and the ocean rises. Then it falls. Twice each day on many coasts, once each day on others, and sometimes in a pattern that mixes the two. You may have stood on a beach in the blue hour and watched a line of foam creep up the sand, then recede, as if the entire sea were breathing. You may have seen mudflats turn to mirror-smooth shallows, then to a silvery plain, then back to open water. The pull feels simple, but the details are lively. Why are there 2 high tides each day, not one? Why does the timing slide by about 50 minutes every day? Why do some places have such gentle tides that you barely notice them, while others have tides so powerful that they pour like rivers and turn bays into rapids? The answer begins with gravity, which is as gentle and as relentless as the moon's light. Gravity is not a rope that tugs on a single point. It is a field that fills space. Every bit of the moon attracts every bit of Earth, because the near side of Earth is closer to the moon than the far side. The moon's pull is a little stronger on the near side and a little weaker on the far side. This difference is the seed of the tides. It is called a tidal force, and it stretches Earth along the line that connects the centers of Earth and moon. Rocks resist this stretch, but water yields. The result is a pair of bulges, one facing the moon and one facing away from it. The Earth spins beneath these bulges, and to a person on the shore, the sea rises and falls. Already there is a quiet question to hold. If the moon pulls water toward it, why is there a bulge on the far side, the one facing away? The answer is not a trick. Earth and moon orbit their common center of mass, the barycenter, which lies inside Earth, but not at the center. In the rotating viewpoint that spins with the Earth-Moon pair, there is an effective outward push, the centrifugal effect, that is the same strength at every point on Earth. On the near side, the moon's gravity toward the moon is stronger than that outward push, so the net is a pull toward the moon. On the far side, the moon's gravity is weaker than the outward push, so the net is a pull away from the moon. That creates 2 tidal bulges. They are not mountains of water. On the open ocean, they are modest, tens of centimeters to perhaps a meter or 2, but the ocean is wide, and a small lift spread over half the planet moves an enormous amount of water. Stand beside this simple picture for a moment. Imagine Earth covered in a deep, uniform ocean with no continents and no friction, a world ocean that can flow freely. In that smooth ideal, the moon would draw 2 steady swells on opposite sides of the globe. As Earth rotates under them, any point would see 2 high tides and 2 lows each lunar day. which is about 24 hours and 50 minutes long. The extra 50 minutes come from motion piled on motion. Earth spins eastward once every 24 hours, and the moon orbits eastward as well, so it takes a little longer for a location to line up again with the moon and its bulges. The pattern is regular, almost kind, with the highs and lows following a clock that slips a little each day. But Earth is not a uniform ocean. Continents break the flow into basins, shelves, and channels. The ocean is shallow compared to Earth's radius, and that means the tides move as very long waves. Shallow water waves that feel the seafloor even in the deep. These waves travel around basins, reflect from coasts, bend under the guidance of Earth's rotation, and form patterns that are more like standing waves in a huge drum than like simple bulges that slide along. In some places, the wave's timing fits the size of the basin, and the response is amplified, the way a swing rises higher when you push at the right moment. In other places, the geometry and timing damp the motion. The resulting map of tidal heights and phases looks like a flower of spirals, with places of almost no tide at their centers and large tides along their edges. There is also the sun, nearly 400 times farther away than the moon, but so massive that its gravity makes a noticeable tide as well. The sun's tidal pull is a little less than half the moon's. When the sun and moon line up, and new moon and full moon, their pulls add. The tides range higher. These are called spring tides, not for the season, but for the idea of springing forth. When the sun and moon form a right angle as seen from Earth, at first and third quarter, their pulls partly cancel. The tides range lower. These are neap tides. The sea is not simply lifted and lowered. It is conducted like an orchestra, with two strong players, moon and sun, and a hall full of instruments shaped by coastlines, seafloors, and the turn of the planet. You can hear the music in the regular misalignments of time. Tide tables drift slowly against the clock on your wall. Low tide on a Tuesday afternoon becomes low tide a little later on Wednesday, and later still on Thursday. The pattern repeats, shifted by the moon's steady march across the sky. If you begin to look for it, you will see the moon and the sea in conversation. A thin crescent sets, and the evening tide follows in its own time. A full moon rises, and a day or so later, the range between high and low increases. Farmers along estuaries still read these signs with the patience of people who work with cycles rather than against them. The feel of the tide is more than a graph. It is the sea's way of touching land. In a spring tide on a wide shore, the water reaches old drift lines and polishes them smooth. In a neap tide, salt marsh creeks fill more gently, the water lingering among the grasses. On rocky coasts, a low tide might expose tide pools populated by anemones, periwinkles, and tiny fishes that shelter under kelp. They wait for the return of the sea, their bodies adapted to hold moisture and to tolerate shifts in temperature, oxygen, and salinity. The rhythm is old enough that evolution has written it into bodies and behaviors. Birds know where to stand to pick off crabs as they scuttle back with the rising edge of the water. Fishermen know when a bar will be passable on the ebb and when it will be dangerous on the flood. If you listen closely, The tide also holds a whisper of deep time. Each tide rubs a little energy from the dance of earth and moon. Friction in the water and in the shallow seafloor converts a trace of orbital motion into heat. The effect is almost unimaginably slight in a day, but over millions of years it matters. Earth's rotation has slowed. The length of the day has increased. The moon has drifted outward, centimeter by centimeter. Fossils hold the story. Ancient corals and shellfish laid down daily and seasonal growth bands that record the number of days in a year. In the deep past, there were more days, which means shorter days, which means a faster Earth. The tides are a subtle break, a quiet exchange between spin and orbit that lengthens our days over geologic time. Tonight, we will be gentle and thorough. We will keep the simple picture of two bulges, because it is a good first lantern. We will also walk the shoreline of the real ocean, where long waves wrap around continents and set up swirls called Amphidromic systems, where some coasts see 2 high tides a day and others see 1, and where certain bays resonate like great bowls. We will meet Newton, who first put the tides into the language of gravity, and Laplace, who framed the tides as waves that travel and reflect. We will touch the mathematics lightly, only as much as we need to see the shapes. We will look at places like the Bay of Fundy, where the sea can rise and fall by more than a house, and places where the rise fits inside a teacup. Take a slow breath. Notice the weight of your body in the chair or bed that supports you, and let your shoulders soften. The moon is up there, whether you can see it tonight or not, and it is reaching across space with a steady hand. In a moment, we will turn back to the first thinkers who noticed that the sea listens to the moon, and we will watch the idea tighten into a thread that runs forward to our tide tables and our harbors today. Long before gravity had an equation, people noticed that the sea paid attention to the moon. Ancient sailors along the coast of India and in the Persian Gulf timed their voyages with the tides. In the Mediterranean, where the tidal range is small, the link was easier to miss. Still, writers like Pliny the Elder noted that the ocean swelled and ebbed with the phases of the moon. In the 4th century BCE, Pytheas of Massalia, a Greek traveler who ventured to the British Isles, described tides that were large and regular and seemed to follow the moon. The pattern was there, but the mechanism was not. For a long time, even great minds guessed wrong. Galileo, who saw moons circling Jupiter and mountains on our moon, suggested that tides came from the sloshing of water caused by Earth's motion. He did not yet accept that Earth spun and revolved at the same time, and he did not see how a distant body could pull a sea. Gravity, as a word and as a law, waited for Isaac Newton. In the late 17th century, Newton brought together the fall of an apple and the orbit of the moon with the same idea. Every mass attracts every other mass with a force that weakens with the square of the distance between them. He used this to explain the orbits of planets, and he went further. He showed that the tides arise from a difference in gravitational pull across Earth's diameter. The moon pulls more strongly on the near side, less strongly on the far side. Subtract the same pull on the center of Earth as a reference, and you are left with a pattern of small forces that point outward on the far side, inward on the near side, and sideways around the edges. This is the tide generating force, a delicate pattern that tries to stretch Earth into an ellipsoid with two long axes. This is a place where a picture made of words can help. Imagine placing tiny arrows on a globe to show how the ocean is being urged to move at an instant by the moon. Directly under the moon, the arrows point toward the moon. On the opposite side, they point away from the moon. Along the sides, at right angles to the Earth-Moon line, the arrows point sideways toward the places under and opposite the moon, as if gathering water to those regions. If the ocean were a thin shell that could slide without friction, it would respond instantly. It would build two bulges along the line of the arrows and keep them there. Newton wrote the mathematics to prove that the lunar tide should have a period close to 12 hours and 25 minutes, half a lunar day, and that the sun should produce its own tide with a similar pattern. He also found that the lunar tide should be about twice the size of the solar tide. The moon's pull on Earth is weaker than the sun's, but the tidal force depends on how the pull changes across Earth's diameter. Because the sun is so far away, the difference between its pull on the near side and the far side is small. The moon is close, so the difference is larger. The result is that the moon dominates the tides, and the sun modulates them. There is one more layer to the far side bulge, the one that faces away from the moon, that people sometimes picture incorrectly. The Earth and the moon circle their common barycenter once every 27.3 days. The entire Earth, oceans and rocks alike, traces a small circle around that point. In the rotating frame that shares this motion, there is an outward centrifugal effect that is the same at every point on Earth. At Earth's center, the moon's gravity and this outward effect exactly balance. On the near side, the moon's gravity is stronger, so the net pulls toward the moon. On the far side, the moon's gravity is weaker, so the net pulls away from the moon. Nothing is being flung off. The ocean is not thrown outward like water from a wet umbrella. These are small differences in steady forces, barely a part in a million of the force that holds the ocean to Earth, but spread across a planet, they move a world of water. Newton's picture is often called the equilibrium tide. It is a baseline idea, a first approximation. It tells you what the tides would do on a smooth, global ocean that could adjust instantly. It is a good lamp. Still, it leaves out time. Water has inertia. It cannot jump and settle without delay. Ocean basins have shapes and depths. Earth rotates. The Coriolis effect bends moving water to the right in the northern hemisphere and to the left in the southern hemisphere, a tendency that is gentle on a river and crucial on a global sea. To bring time and shape into the picture, we turn to Pierre Simon Laplace, an 18th century mathematician and astronomer who wrote down equations for how the sea's surface moves under small forces when the planet is spinning. Laplace's tidal equations treat tides as waves that are forced by the tide-generating potential of the moon and sun. These waves are very long. In deep water, their speed is set by depth and gravity. A simple formula, the shallow water wave speed, says that long waves travel at roughly the square root of g times h, where g is gravity and h is the water depth. In a 4-kilometer deep ocean, that speed is about 200 meters per second. Around a continent shelf, where the depth is tens or hundreds of meters, the speed is slower. The tides you experience on a coast are not water racing around the world at the speed of a jet. They are the rise and fall of a long wave as it passes your shore. A wave that is steered by depth, reflected by land, and curved by rotation. This is why the map of tidal phases looks like a pinwheel of gentle spirals, centered on places called Amphidromic points. Around each of these points, the tide rotates, and at the exact center, the tidal range is near zero. Move outward along the arms of the spiral, and the range increases. The shape and location of amphidromic systems are set by basin geometry and Earth's rotation. In the North Atlantic, there is a counterclockwise rotation. In the North Pacific, another pattern, and so on. When you stand on a pier and watch the water rise, you are seeing a shadow of these invisible gears, the long waves turning around centers far out at sea. Certain coasts and bays become theaters where the tide's performance is amplified. The Bay of Fundy, between New Brunswick and Nova Scotia, is shaped like a channel that narrows and shoals as it reaches its head. The timing of the lunar semidiurnal tide, the twice-daily component, is tuned close to the natural period of oscillation of the bay. Each new pulse from the ocean arrives in phase with the bay's own slush, and the height builds. Tidal ranges over 12 meters occur in places there, enough to expose cliff faces and leave fishing boats resting on the bottom at low tide. Other places, like the Gulf of Mexico, often have a tide that looks more like a single rise and fall per day, a diurnal tide, because the mix of forcing and basin shape favors a daily component and suppresses the twice-daily one. As the moon orbits, its path tilts above and below Earth's equator. This declination shifts the symmetry of the tide, so that two daily highs are not equal. The inequality is small near the equator and larger at mid-latitudes when the moon is far north or south. This is why, on many coasts, one high tide is a little higher than the other, and one low a little lower. The precise pattern depends on where you are, how the amphidromic systems send their rotations into your basin, and how local coastlines shape and delay the wave. The sun's role is quieter but distinct. Alignments produce spring and neap tides, a fortnightly rhythm that rides on top of the daily and twice-daily patterns. When the moon is at perigee, its closest approach to Earth, the lunar tide is slightly stronger. When it is at apogee, it is slightly weaker. Over 18.6 years, the tilt of the moon's orbit itself precesses, changing how far north and south the moon reaches. This nodal cycle alters the tendency toward diurnal or semidiurnal tides in many places, and careful tide records reveal its slow sway. There is something tender in how all of this fits without hurry. Newton's insight about gravity sets the stage. Laplace's equations add motion. The Earth's rotation leans the flow, and basins give the music a room. The moon is small next to the sun, and the tides are small compared to the ocean's depth. Yet together, they create a daily rearrangement of water that shapes life on coasts around the world. In the next part, we will deepen the science gently. We will step into these long waves and feel how they hug coasts, how they spin around amphidromic points, and how their energy moves from the surface into the interior as internal tides that climb underwater mountains. We will visit harmonics, the way tide records are decomposed into a family of constituent rhythms, each with its own astronomical source. And we will walk to the edge of a tidal bore and listen to the sound of a river beating the sea in a moving wall. Let us begin with motion seen from above. Imagine the ocean as a broad blue membrane that can rise and fall slightly. The moon's tide-generating pattern presses gently on this membrane, and long waves begin to move. Because Earth rotates, these waves feel a sideways lean. In the northern hemisphere, a long wave that travels with the coast on its right, looking in the direction of motion, can be trapped along that coast. This is a Kelvin wave, a coastal cousin of the broader tide. It moves with the shoreline, its crest the highest at the coast and decaying offshore. In a wide basin, these trapped waves can run along the edge, turn a corner at the basin's mouth, and continue along another shore, always keeping the coast to the right in the north, to the left in the south. Where a basin is like a bowl, the tide behaves like a standing wave. It sloshes back and forth with nodes and antinodes, points of little motion and points of larger rise. The period of this slosh depends on the basin's length, depth, and shape. If the astronomical forcing has a period near one of these natural slosh periods, the response is large. The Bay of Fundy is tuned in this way for the twice-daily tide, and the resonance lifts the range. In other places, the tuning is off, and the response is muted. A harbor can have its own tone, a small echo of the bigger basin. Engineers who design ports study these tones to avoid problems like Seychelles, the harbor's version of a lingering slosh that can complicate docking and loading. Amphidromic points are the quiet centers of whirling tide systems. Around each one, the phase of the tide advances smoothly. If you could drop a ring of floating markers around such a point, it would rise in sequence, like people standing to wave in a stadium, the crest traveling around while the center remains nearly still. The number of these points and the direction of rotation around them depend on the size and shape of ocean basins, and on how the long waves are forced and reflected. They are not fixed forever, but they are steady over many years unless seafloor or coastlines change in large ways. Now bring your attention downward under the surface, where tidal currents flow over underwater ridges and seamounts. They can generate internal tides, waves that travel along density layers within the ocean rather than on the surface. The ocean is stratified, with lighter, warmer water above and denser, colder water below. Internal tides have large vertical motions at the boundary between these layers, yet their surface expression can be subtle, a barely visible line of rougher water that passes like a wrinkle. Over thousands of kilometers, internal tides carry energy into the deep, where they break and mix the ocean, lifting nutrients and influencing the global circulation that slowly moves heat and salt around the world. The moon, through tides, is one of the engines of this interior mixing. Tidal bores are another special case. In narrow, shallow estuaries that open toward regions with large tidal ranges, the incoming tide can bunch into a steep front that travels upriver as a moving wall. The Severn boar in England, the Qiangtang boar in China, the Pararoca in the Amazon, and the boar on the Petitcodiac that feeds the Bay of Fundy are all famous. At high spring tides, you can hear them before you see them, a growing roar that resolves into a sudden rise. Surfers sometimes ride them for kilometers, moving inland as the river's normal flow is temporarily reversed. A boar is a reminder that tides are not only heights on a chart, but currents with momentum that reshape the meeting places of river and sea. Scientists and mariners describe tides with a language of constituents, harmonics that each represent an astronomical clock in the sky. The largest is the lunar semidiurnal constituent, often called N2, with a period of about 12.42 hours. There is a solar semidiurnal component, S2, with a clean 12-hour period. There are diurnal components, like K1 and O1, with periods near a day, that reflect the tilt of the moon's and sun's paths relative to Earth's equator. There are small corrections from the ellipticity of orbits and from the nodal cycle. A tide gauge records a curve that looks complex, but this curve is the sum of a few dozen smooth sine waves. Over months and years, one can fit these constituents, estimate their amplitudes and phases for a given harbor, and then predict tides years in advance. Tide prediction machines built in the late 19th and early 20th centuries did this mechanically, with pulleys and chains that added waves together. Now computers do it in moments, but the principle is the same. The ocean is a resonant instrument, and astronomy supplies the notes. The moon and sun do not act alone. Weather rides on top of the tide. Low atmospheric pressure allows the sea surface to rise slightly, about a centimeter for every millibar drop in pressure. Strong winds can pile water against a shore. When a spring tide coincides with a storm and the seasonal cycle of sea level, the result can be a storm surge that floods coasts. These events are not new, but they sit on a slow rise in mean sea level, driven by warming oceans and melting ice. Reading a tide chart, a barometer, and the sky together is an old art. It remains a living practice for people who live and work near the water. Not all coasts face the tide in the same way. On the U.S. West Coast, the Pacific brings a mixed tide with too high and too low waters of unequal size most days. In parts of the Gulf of Mexico, the diurnal component dominates, and one high and one low water mark the day. The North Sea, bounded by coasts that funnel and reflect long waves, has strong semidiurnal tides that run like rivers through channels between islands. The Mediterranean, nearly enclosed and with a restricted connection to the Atlantic, often shows small tides in height, though currents can be strong in narrow straits. Each place is a conversation between the global forcing and local geometry. A good way to feel the physics without equations is to think of the tide as a choreography of compromise. The moon and sun set a pattern that repeats. The ocean tries to follow. Earth's rotation leans the flow sideways, and the coasts and seabed say, yes, but this way, and sometimes not quite yet. The result is a pattern that is stable enough to chart and complex enough to be interesting. The currents that flood and ebb through a harbor mouth may veer a little earlier or later with changes in wind and weather, but their main beat follows the quiet clock of the sky. There is one more gentle layer, the connection to the solid earth. Rocks deform under load. The land itself rises and falls by a few centimeters with the passage of the tide, pulled elastically by the moon and sun. This earth tide is not easily noticed without instruments. Yet in some places, it slightly changes the strain along faults. In ice sheets, the flexing can modulate how fast outlet glaciers slide. Even in the deep crust, the twice-daily stress change can be measured. The whole planet participates in the rhythm, not just the sea. In a moment, we will step back to see how this rhythm shapes life. The intertidal zone is a place of invention, where organisms endure air and water, heat and cold, in periods of feast and famine. The tides drive mixing, carry larvae to new homes, and set the timing of migrations and blooms. They also thread through our own history, guiding fishing, trade, and the placement of cities. The same force that slows Earth's spin also slowly pushes the moon away, and in the deep past and distant future, the pattern of the tide will not be quite the same. Holding that span in mind can make the sound of today's waves feel even more precious. Walk out onto a tidal flat at first light. The mud is patterned with ripples that run in soft ranks, each one a frozen memory of the last ebb. Small crabs leave hieroglyphic tracks. Eelgrass lies draped in lines that show where the water paused in its retreat. This is a laboratory of survival. Barnacles close like little doors when the air dries. Mussels and oysters hold a sip of sea to carry them through the hours. Seaweeds are built to stretch and bend. Snails carry their homes to keep their insides moist. Even fish have learned to use this shifting ground. Some, like mudskippers, can breathe air and climb, blurring the line between water and land. Tides are clocks for these lives. Many creatures spawn or release larvae to coincide with spring tides, when currents can carry offspring farther. Horseshoe crabs climb beaches on high spring tides in late spring to lay eggs in sand where waves will not strip them away. Shorebirds time their migrations to harvest those eggs, a feast that fuels long flights. In mangrove forests, the shape of the trees, with arching roots that stand like stilts, comes from the need to breathe in mud that is often waterlogged. The twice-daily inflow and outflow are like a breath that the forest takes, bringing oxygen-rich water and carrying away waste. In the open ocean, tides stir and mix. Where internal tides break on rough topography, they pull cold, nutrient-rich water upward. This feeds plankton, which feeds fish. Fisheries along some shelves benefit from tidal mixing fronts, places where water masses meet and nutrients concentrate. The moon's steady pull is part of the engine of productivity that makes the sea generous. It is not the only driver. Winds and the broad thermaline circulation matter too. Yet without tides, the ocean would be more layered and less connected. Humans live by the tide in countless quiet ways. Harbors are dredged with the timing of currents in mind. Bridges are built with clearances that consider the highest astronomical tide. Pilots who guide ships through narrow channels learn the feel of a flood and an ebb through their hands on the wheel. Fishers plan nets and traps with the turn of the tide. People who farm salt gather brine into shallow pans, and let the sun and wind do their slow work, opening gates on the flood and closing them on the ebb. In places with large ranges, simple ramps can serve as dry docks. Boats settle into cradles on a low tide, and work proceeds on hulls that will float again when the tide returns. There is also the old dream of harnessing tidal energy for electricity. Tides are predictable, which makes them appealing. There are two main approaches. One is to place turbines in tidal streams, where strong currents race through constrictions. The other is to build tidal range projects, basins with gates that fill on the flood and empty through turbines on the ebb. Both have environmental footprints, and both work best in places where nature already amplifies the tide. The physics is kind, the engineering is careful, and the economics depend on local geography. Where used thoughtfully, tidal power can be one part of a mixed energy future, an echo of the moon's pull turning into light in a home. The moon's pull affects stone as well as water. Over hundreds of millions of years, the friction of tides has changed the Earth-Moon relationship. Each tide dissipates a little energy as heat in shallow seas and along coasts. Conservation of angular momentum links Earth's spin and the moon's orbit. As Earth loses spin, the moon gains orbital energy and moves outward. Laser reflectors left on the moon by Apollo astronauts let us measure this recession directly. The moon drifts away by about 3.8 centimeters per year. Fossil corals and bivalves tell the same story in another language. They grew daily bands and seasonal patterns that reveal how many days fit in a year long ago. In the Devonian, hundreds of millions of years ago, there were over 400 days in a year, each day shorter than now. The tides have been slowly lengthening our days and pushing the moon outward, a process that will continue gently for a very long time. Tides also shape moons elsewhere. Io, a moon of Jupiter, is heated by tides raised by Jupiter and by the tugs of neighboring moons that keep its orbit slightly eccentric. The constant flexing warms its interior and feeds volcanoes that paint its surface sulfur yellow. Europa and Enceladus, around Jupiter and Saturn, likely have oceans kept liquid by tidal heating beneath ice shells. Plumes jet from Enceladus, water meeting vacuuming bright arcs that hint at chemical energy and perhaps, someday, the conditions for life. Here, the tide is not a surface wave, but a kneading of an entire world. On the other side of the balance, tides tend to lock spins. Our moon keeps one face toward Earth because over time, tidal friction in the moon's interior slowed its rotation to match its orbital period. Many moons in the solar system are tidally locked to their planets. Even planets around close-in or dim stars can become locked, turning one face forever to their sun. On such worlds, the concept of a day is different, and the meaning of a tide would change. The physics is the same, but the stage is set differently. The Earth-Moon system itself does not sit still inside Earth. The barycenter, the balance point of their shared gravity, lies about 3/4 of the way from Earth's center to its surface on the line to the moon. Earth orbits this point each month. The trace of that motion shows up in the paths of satellites and in the precise timing of signals. The sun pulls on Earth and moon together, and the entire dance writes a graceful pattern in space, a rosette whose petals repeat with subtle changes. The tides are the touch that carries inside Earth and ocean the same pattern written outside in space. It is soothing to see how the same idea of a difference in gravity can explain so many things. Two bulges on a shallow sea, a slow drift of our days, hot ice moons with hidden oceans. Even the way stars can be tidally disrupted if they pass too close to a black hole, torn into streams that glow as they fall inward. These are wide ranges of scale for the same kind of physics. When you stand on a beach and feel the pull of water around your ankles on a flooding tide, you are physically connected to a story that reaches to Io's volcanoes and to the rings of Saturn. The moon's influence is not mystical. It is specific and measurable. Yet there is a human feeling that comes with watching the tide that mathematics alone does not fill. The regularity and the change, the high that is never exactly the same as last time, the low that reveals and then conceals, these feel like the way days pass. We are not pulled by the moon in our moods in any simple way, but we can let its rhythm remind us to keep a patient watch on our own cycles, on rest and activity, on taking in and letting go. Soon we will come to shore and carry what we have learned into the ordinary day. We will look at tide tables with clearer eyes, trace spring and Neap on a calendar, and think about safety on coasts where the sea moves fast. We will remember that weather rides on tides, and that sea level is slowly rising, which changes the meaning of familiar numbers. We will keep the physics as a comfort more than a warning, a way to know where we are in the long rhythm that has run since before we had words for it. It is late or early where you are. The moon might be up, or it might be below the horizon, and still the tide keeps its time. If you live near the coast, you can make this knowledge practical and gentle. Look up the tide table for your nearest harbor. You will see columns of times and heights, often 2 highs and 2 lows each day, with a slow fortnightly swelling and shrinking. Notice how the times slide by about 50 minutes daily. Mark the next new moon and full moon on your calendar, and watch how the ranges widen in the days around them. If you are far from the ocean, find a river mouth on a map and imagine the tide moving inland, slowing against the river's flow, sometimes forming a bore, sometimes only a quiet reversal. Walking with the tide can be a way of walking with attention. On a spring low, you can visit tide pools and look into a small universe. Please step carefully. Everything there is living space for someone. On a flood, you can watch currents form around pilings, small standing waves that lean downstream and glisten. If you are a swimmer or a kayaker, learn the local currents as well as the heights. In some places, the main hazard is not the water level, but the speed and direction of the flow. Slack water, the brief pause between ebb and flood, does not always coincide with high or low tide height. Local charts and local knowledge matter. The science you carry in your mind can shape your safety without weighing on your heart. If a high spring tide coincides with a storm forecast, imagine the pieces coming together. Lower pressure lets the sea rise a bit. Onshore wind piles water. The astronomical high arrives. Each piece is small, but together they can lift the water into streets that are used to being dry. This is not a reason for fear. It is a reason for readiness. People have lived with tides for as long as there have been coasts. What is different now is the slow rise in mean sea level. A tide height that used to be rare becomes more common. A tide height that once stayed below a seawall now brushes its top. We can respond with care by planning, by restoring marshes that buffer storm surges, by listening to forecasts with an ear trained by understanding. When you read a tide chart, you are reading a sheet of music written by the sky and played by your shore. The largest note is the lunar semidiurnal tide. The sun adds a harmony. The shape of your bay adds an accent. The weather adds a temporary variation. Once you hear these parts, the tune becomes familiar. The half-hour slip from one day to the next stops being a surprise. The neap tide becomes a calm within the cycle. The spring tide becomes a reminder of alignment, not of danger by itself. Only an awareness that more range means more change to watch. If you enjoy numbers, you can take one more step. Many weather agencies publish harmonic constituents for local stations, the amplitude and phase of M2, S2, K1, O1, and more. If you add those sine waves together on a simple spreadsheet, you can reproduce the tide curve that the official table shows. There is a pleasure in seeing the curve rise under your own calculation. It makes the moon and sun feel both grand and near. If you are not a numbers person, the same satisfaction can come from walking the same beach at different phases and letting your body learn the pattern. Where does the rack line fall in a neap? Where does it reach in a spring? Where is the safe crossing on the flats? And when does it cease to be safe? The tide links us to places we have not yet been. When you watch a high tide fill a Cornish harbor, you can imagine water rising at that same moment along the coast of Brittany across the channel. A little later or earlier, depending on the turn of the phase around the Amphidromic points in the North Atlantic. When you watch mud gleam under a winter moon in the Wadden Sea, you can imagine that same moon lifting water at Fundy and in the Beagle Channel. The continuity is soothing. The ocean is one body, and its breath travels, reshaped by shores, but always present. There is kindness in knowing that the force behind this is small. The tide-generating acceleration is a tiny fraction of the gravity that holds us down. It is the difference across a planet that matters, not the absolute pull. Something delicate, integrated over time and space, becomes visible. That is a good pattern to remember in other parts of life. Small, steady influences, applied in the same direction for a long time, can reshape a landscape. It can be your sleep schedule, your practice at a craft, your way of attending to the people you care for. The moon does not yank the ocean. It suggests. The ocean answers. At the edge of sleep, you might picture the two bulges as soft swells that slide under the turning earth. Not rigid, not in lockstep, always leaning and lagging as waves do, and you can let that motion carry your breath. In the light of morning, you might picture the tide as a clock that you can consult, part of how you set your day if you live by the sea. The physics stands calmly in the background, precise and untroubled, never demanding, always available when you want to look closely. The view can be as simple as a rising line, or as complex as a map of spirals and resonances. Thank you for spending this time with Hypnosphere, and for letting the moon and the sea fill a piece of your evening or morning. If this quiet journey through tides helped you relax or sparked a softness of curiosity, you are warmly invited to subscribe. There will be more nights like this, more gentle explorations, more chances to rest with science, and to feel the world a little more clearly.